So Doug Britton, I'm one of the founders at RunSafe, and I made my bones working amongst some organizations that were up here speaking earlier, sort of facilitating access to intelligence objectives, and wanted to figure out how our adversaries have a bunch of very reliable methods that they use. And how can we break up their economics? And Jen was talking about it this morning. I don't have I'm not going to solve a Rubik's Cube while I talk, but I will play with a stress ball. So, how can we deprive the attackers of a very reliable series of methods? So, the 0-day problem. Okay. 0 days are like this bogeyman in cybersecurity, and we're plagued by them, and they're a part of advanced persistent threats, and they're actively exploited in attacks. So, and in the embedded space, the situation is much more acute for a couple of reasons. One, in the embedded space, there's much less interpreted code. And in the embedded space, you have each of the individual devices has far less of a protective perimeter around it. So, the much more of the code is compiled, C and C++, and as a percentage of the volume. And so, this memory safety is a much bigger risk. And testing hasn't found all the bugs, because if it had found all the bugs, we'd have found all the bugs. So, is there a way that we could reduce the exposure before the next 0 day is discovered? So that's the question that, if you could solve it, it'd be somewhat akin to sort of solving aging. So let's understand return-oriented programming. All right, and we're going to do this early in the morning, Monday morning, by jumping right into Binja. So, okay, let's take a different route. Let's take a couple of analogies. We're going to start with Moby Dick and then move to bank robbery. So, a memory safety crash course. So this block of text is from a first edition of Moby Dick. And as many of, I'm sure you do, have your own first edition of Moby Dick, you probably remember that it has 635 pages. And why this is interesting is if I'm going to use, if I'm going to use a text, what a memory safety attack is taking characters in a text and using it in an unintended order. And so since we all have our first edition Moby Dick, what we're able to do is look at, page 1, row 1, word 3, letter 1, row 6, 3, 6, do this iteratively, and I'm able to create my own text out of this. It says, I'm a hacker, I have your data, please wire the money to. So what I've done is I've taken legitimate text and used it in an unintended order, and I've generated my, my ransom note. So that's exactly what a memory safety attack is. I'm going to take legitimate code. I'm going to take, the instructions that are legitimate and the data and the opcodes to those instructions, and I'm going to misuse them, stitch them together in an unintended order. And this is a sample of a piece of binary, breaking out the assembly level functions and what are the pieces of what's called a ROP chain, or return-oriented programming chain, getting stitched together in an unintended order. So right here, though, is the money shot. This one line in function 4, it says call system. And system is the use of operating system resources. That could be writing a file, that could be opening a port, that could be a lot of things. That's in any attacker's goal is to misuse syscalls. So now bank robbery. Now if we look at a schematic of a bank, like what's the goal in robbing a bank? I mean, typically to get into the vault or to get something in the vault to come out to you in some fashion. That's the whole job of a bank robber. So what are the vulns here? I mean, you've got windows that you could break, you've got guards you could bribe, you've got ATMs you can do something with, and ATMs are cool, but that's a lot less money than is in the vault. So if we get in the business of looking at all of the vulns. What are the million ways that you could try and get into the vault? This is kind of akin to software testing, where we're trying to find what is every little overflow here, every little overwrite, and have we really protected the vault? So are there ways that you could start hardening the vault? So one of the first things you'd do is you'd remove all the meat sacks, which are often one of the easiest ways in. They're the easiest to bribe. What else you would do is you'd get rid of the windows and you get rid of the glass door. Okay, so how does this have anything to do with software? So that vault is the syscall in Linux. It's other things in other operating systems. But the whole thing is get to the syscall and have maximum influence over the registers that are the input to that syscall. And that sets up the ability for remote command injection, which is the bane of all software. Remote, not needing to touch a system, sending packets, and having ownership of the box. So, is there a way of protecting the vault without worrying about all the vulns? So back to the real world. So what are ROP chains? In the olden times, 2006 and before, the whole purpose of the memory safety attack, or the typical practice, was you'd have an overflow, you jam your payload into that overflow, and you'd be able to execute that. Yeah. Now, that's less applicable today because of DEP, NX, and other protections. So now the job is, again, what we've been talking about, return-oriented programming, where I'm going to take legitimate slices of code and misuse them. And so now the attacker's job is to dig through and figure out what are the ways that I can stitch this together to get to a syscall. Again, you could find a series of paths moving around data amongst registers and just go in and, a longest traveling salesman route of overwriting registers. But why? You're not doing this simply for fun. You're doing it to make the vault door open or to own the phone. So you're targeting a syscall, again, in Linux. So in ROP chains, we come back to code we referred to earlier. We're looking at snippets of code from function 4, function 7. You put those pieces, those exact assembly instructions, which we might do some bit shifting on, and combine that with a bug that allows a smaller overwrite that redirects something to misuse these instructions, and then you have a complete exploit. So now, is there a new way of trying to figure out what is the risk here? Because most attempts at securing software, again, are looking at the vulnerability side. They're testing, can we find all the vulns? That's a demonstrably hard problem, and we haven't solved it yet, again, because if we did, we would have, and all the bugs would be gone. Can we ask a slightly different question? And can we assess the useful chains to an attacker? And given an exploit, what can an attacker do? So, so then we start a type of analysis that we worked on in partnership with Ulf Kargen at Swedish University. And we say, now let's understand each of the syscalls. And then let's understand what is, via essentially a form of taint analysis, what is the influence that can be had over that syscall? What do we get control of the input registers? And do we have, in this case, mprotect, which is a very dangerous syscall that lets you change memory permissions? Can we get flags into it that let us change it from read execute memory to read write execute memory, in which case you now get to do what you want with memory. Again, instead of finding all the windows we can break to get in, let's look at the vault and figure out from there what are all the ways that vault can get misused and work out. So, and in this particular, in a particular binary, we do this syscall-based risk ranking. So we look at how dangerous are the syscalls that are available to the attacker. There's 31 syscall models. We'll look through them in more detail in a second. There's a syscall combos, and we look at them in a severity starting from, does this syscall, if you get influence over this with a vuln, can you get remote command execution? Can you get remote file system manipulation, which is, the ability to modify like Etsy Shadow remotely? Can you do local file system manipulation? This is a more complex attack for the attacker because they need to get something on the device and then they need to get somebody to run it, but still extremely dangerous. And then, limited file system manipulation, unlinking or deleting files. So, and then no syscalls. So in this capacity, what we're able to do is analyze a binary and say, presuming a vuln, what can be done? And in looking at, in this case, the Yocto, a specific Yocto build, what percentage of the ROP chains, 15.6 million ROP chains found that, presuming a vuln, become weaponizable. So what percent give remote command execution, remote file system manipulation, et cetera? So, and this is asking a different question, and that's giving a novel insight. So the prior question was, can we find and test all the bugs? No. Okay. Instead of then stopping and saying, okay, well, there's nothing we can do, we say, okay, what is the thing that we can understand? And 0 days are present. It's statistically inevitable. What damage can they do? And is there mitigation that's possible? So now that we can quantify the risk, what can be done about it? So there's a lot of work that's been done. Microsoft published papers a while ago, now nearly 20 years ago, in control flow integrity. There are things being done by the various chip manufacturers, memory tagging extensions, other things. There's fine-grained randomization. What these kind of things can be done that are independent of the software to mitigate risk. Okay, but Rust. And Rust solves all the problems, except so in our organization, we've done a lot of work with military programs that are trying to deploy Rust, and we've talked to a couple of the system assessors that have responsibility for testing the software, and 100% of the programs that have been submitting weapons platforms or other things using Rust have all used Rust in memory unsafe implementations, like 100%. So you take the optics one way, oh, they're using Rust, everything's cool. Not cool, not done, because it's a memory unsafe implementation. And vulns have existed in Rust. They're far fewer, but they exist. If you combine the vulns that exist and memory unsafe implementations, and what one analyst put together is like the 17 to $64 trillion it'll take to rewrite everything, that's not a complete answer. So, so detailed perspective on one in situ protection is load-time function randomization. So what this does, instead of a binary getting loaded sequentially in memory every single time, and instead of ASLR, address space layout randomization, which every time it loads, the binary as one contiguous block gets loaded in the same place, let's take the assembly level functions and break them up. Every time the binary loads, those will have a different layout. And the average binary has 280 assembly level functions. And this is not like a printf definition. This is, once it's compiled, it's broken down into 10, 100 functions per text function. And that gives you 280 factorial possible memory layouts, which is roughly 10 to the 400th. So, and if we go back to this piece of binary that we've come to a few times, the attacker is counting on ROP gadgets, or the individual highlighted blocks that are crossing function boundaries. And as the first speaker was talking regarding MIPS, the Volncheck CTO, I apologize. I forgot his name, but I was doing the math on the address spaces he was presenting, and all of those ROP chains were crossing. There's no way that was one contiguous function. Like, those were crossing function boundaries. And so by crossing function boundaries, that deprives the attacker of the ability to use those ROP chains. And if we go back to the risk model that we described earlier, remote command execution being the most risky, remote file system manipulation being less risky, what we're able to do, and this is on an actual binary, analyze like what's the risk reduction in exec Vs. And it's 99.59%. So, and for the top class, it's an average of 99.73% risk reduction in, what an attacker can do with, remote command execution. So what that means is that, the next 0 day, which again is a statistical inevitability, that next 0 day is not going to have a statistical likelihood of being able to do remote command execution. You're going to need 10,000 0 days, and maybe a few of them, of those 10,000, will now be able to run some kind of remote command execution. And so it's a specific quantification of the risk, and you can take, so here we did a detailed analysis of an in situ load-time function randomization. You can do the same thing against control flow integrity and memory tagging memory tagging extensions, and come up with what is the reduction in the actual risk, and then set that against complexity for the developer, et cetera. So what we've gone from is, we've now given, programs a way of measuring the kind of risk that are in their binaries. We're, able to help them understand that, this legacy software that, Jen and Andy and everybody recognized has catastrophic risk, and able to assess what is our ability to reduce that risk by a bunch of, again, in this case, in situ protections, and turning unknowns into quantified mitigated risk. So, questions? Sir.
Thanks for the talk. I got fixated a little bit on the Rust segment, specifically because I think there's a bit of a philosophy problem maybe within software engineering. So Rust in unsafe implementations, as far as I'm aware, and the dabbling that I've done with it, tends to exclude, for example, inter-process communication or like virtual memory mapping between processes as viable solutions for software. And so in order for Rust to be holistically like unsafe, right, and those those code sections are explicitly tagged as unsafe, has there been any movement in the industry or like an agreed upon solution of like how do we get away from those specific behaviors so that we can instead focus on just a strictly Rust safe implementation? Does that make sense?
My answer will tell you if I followed. So what we're seeing, we work with a lot of embedded device manufacturers that have tens of thousands, hundreds of thousands of devices deployed downrange, and they're looking at the complexity of getting Rust, like an entire Rust stack from the first electrons through memory, through the time it powers back down. And what they're the best estimate of most of them, it's like 8 to 15 years. Even if magically all the code could just get rewritten, which we're several scientific breakthroughs away from that being possible or being practical. We're a decade away from a complete implementation stack. So even if you write your complete software, all your deployment in Rust, you still are on top of the Linux operating system. And so anytime you hit libm, libc, the same set of risks exist. So, I don't know. I know that there is, Rust is gaining speed in universities as a basis of, when I learned, when I did my bachelor's, everything was simply C, and we took a C++ class. Now, Rust, for many universities, is the first language you learn, so that's encouraging. And I know that's not it's a non-rigorous anecdotal perspective on your question, but it is, there's a lot of things that are not yet standardized in Rust. We do a lot of work in the safety critical space also, so aircraft, vehicles, and getting a standard definition of good form of code in Rust that would be testable against the safety standard is not there's not a uniform answer to those kind of questions yet. So, I think the fact that it's getting as much focus as it is exciting, but you're also still suffering from a talent deficit. We need, for Rust to promulgate as quickly as we'd like, we need roughly 100 to 150 times as many Rust developers as we have, at least, and that will take a long time to cover. So I don't have a good answer. There's no right click to that one.
I think it was an excellent answer. Thank you.
Yes. Crushed it.
Sorry, there's.
Oh, here we go.
Hey, about the load-time function randomization.
Sure.
Is that something that operating systems are implementing, or that's actually happening on the processors themselves? And sort of what's the status of that?
Yeah, so it's a body of practice that, RunSafe, we work with operating system manufacturers. We have partnerships with several real-time operating systems. We work with several operating systems. So it is something that, our customers have been able to implement, again, from the first electrons across the processor to the application space, and that's enabling the, one of the problems is if the operating system doesn't implement something like that, again, if the vuln is in your proprietary code, your proprietary code is on average less than 2% of the code volume on an embedded device. So the attack path is generally exploit a vulnerability in your code to get libc to do something inappropriate. So by building the protection into libc, even if your 2% of code by volume isn't protected for some reason, you're still getting the full benefit of the protection. So it is something that, and I can happy to discuss with you the operating system providers that are putting it in, but yeah, it is getting woven into several operating systems.